Right, hi guys. We're covering chapter 16, static electricity. This is the first chapter in your electricity and magnetism portion of the study of physics. Alright, the breakdown is that there will be three main portions that we have to cover. Alright, there are some big differences between the combined science and the pure physics students. So I will just highlight to you. The combined science students, actually this portion is not necessary for you. Alright, this portion and some of this portion is necessary for the combined science. The pure science students you have to cover. So the combined science will just be about 50% of the chapter will be covered. So I'll just tell you which one is relevant, which one is not relevant later as the video progresses. Alright, so these are some of our learning outcomes. Right, before we begin, I want to show you a short video of static electricity in action. Right, you can see the girl is using her blanket and rubbing the dog, and the dog's hair is all standing up straight. Alright, I got one more short video to show you about levitation of a balloon. So let's have a look. I'll link the video in the description so that you can also have a look at it. So the student is rubbing the balloon on the hair. So when he places his hand up, right, you can see that the balloon is attracted to the hand. Alright, so when he moves his hand around, it will be attracted to his hand. Alright, so let's look at it. Alright, and the balloon is moving towards him now. Alright, so these are all effects of static electricity. I will show you another portion of static electricity, which is the Wimshurst machine. So just hold on, I'll let you all see the Wimshurst machine. Hi guys, what I have here is a Wimshurst machine. Right, so what this machine does is basically it builds up charge. You see these two big things here, these are capacitors. Capacitors are basically things that can hold charge. Alright, so if you look on this side, and you look at all of this, you can see that when I spin this item, let me see if I can get a better angle for you. When I spin this, you can see this metal piece actually dragging along and hitting this, the metal piece that are all there. So when it does that, it causes the charge to build up. Then the charge is stored inside these two capacitors, and when there's enough charge, then you will see something amazing happen. Okay, so let's try it. I'm going to build up some charge. Don't know whether you caught it. Yep, so you have basically a spark going from one of the orbs to the other orbs. Alright, sometimes you cannot see because I think the camera cannot capture it. Right, so this is basically exactly the same as what happens in lightnings. So in what happens in lightning is that the clouds, you have a lot of these water droplets and you have a lot of these ice crystals. They rub against one another, just similar to how this is rubbing against the metal piece, and it will cause the charges to separate. So once you have enough charge to separate, you will induce something called dielectric breakdown. So what is dielectric breakdown? It's just basically each material has a different number for this dielectric breakdown. So it tells you how much charge. If you have enough charge, then that insulator here, got static. So the insulator here, which is the air in between, will actually act as an insulator once you reach, the air insulator will act like a conductor once you reach the dielectric breakdown. So later on, I think for the pure science students or the pure physics students, you will learn about the formation of charges via rubbing. The combined science student, not so much. Right, so just one more last try. If you want a bigger spark, then you have to make the air get bigger. Yep. So that is Wimshurst machine and generation of sparks for static electricity. Right, so that's why we have a lot of countermeasures to build up or sparks. Later on, I will cover in a bit more detail at the later end of the video. Alright, thank you. Bye-bye. Alright, so now that you have seen all the effects of static electricity, it's time to go into the details of it. Before we begin, we need to recap on some of your set 3 chemistry, atomic chemistry. You must remember that matter is made out of atoms, and atoms are made out of subatomic particles. called the neutrons, protons, and electrons. And the protons are positive, electrons are negative, neutrons are neutrally charged. Right? In the nucleus, you only have protons and neutrons in it. So the overall charge of only the nucleus is positive, because there's only positive particles and neutral particles. The electrons orbit around the nucleus. So as a whole, when I look at the atom as a whole, then the charge, the positive and the negative charges balance out each other, and the atom is neutral. Alright, to make an atom positively charged, the only way I can do it is to remove electrons. And if I want it to be negatively charged, I need to add electrons. If the number of electrons and protons are equal, then the atom is in a neutral state. Alright, why is it that I cannot say that we're going to add a proton inside this? In theory, you can, or why can I not remove a proton to make it negatively charged? Alright, you can, but that goes into the study of nuclear physics, which is not what we are studying today. Alright, so just take note, when I want to make something positive, I remove electrons. When I want to make something negative, I add electrons. Right, so how do positive and negative charges interact? This one I put like 4 stars here, because literally this is the single most important thing in this chapter. Anything that appears as an explain question, they ask you explain why this happens, and you know it's a static electricity question, one of these two is the answer. Alright, light charges repel, unlike charges attract. Take note, charges, it is common for students to write poles here because they are quite used to talking about magnets, but please make sure that you write charges instead. Alright, now the SI unit of a charge is a Coulomb, written with a big C when you're writing the units. 1 electron carries a very small amount of Coulomb. Alright, 10 to the power 19. 10 to the power negative 19 Coulomb, sorry. So it's a very small amount. So for you to make up 1 Coulomb of charge, you will need a lot of electrons. The order is 10 to the power 18 electrons in 1 Coulomb of charge. Alright, so now we are going to go into the part where there is some differences. So just take note, how do things get charged? The combined science students, you do not need to know how things get charged, but you do need to know the movement of charge. So for this portion, everything I cover here will be covered, but the next slide onwards, only the pure science students will need to listen in. Alright, there are 2 ways in which things get charged, and that depends on what kind of classification of material it is, whether it's an insulator or whether it's a conductor. Alright, an insulator, the particles are not free to move around, while in a conductor, the particles are free to move around. Alright, so you can just see the insulators cannot conduct electricity while conductors can. And the way we charge insulators is by friction, and the way we charge conductors is by induction. Right, you later on we will go into detail what each of them are. Combined science students, you do not need to know this. Right, some examples of insulators: glass, silk, and wool. Conductors: copper, iron, the usual metallic stuff. Alright, so just for you to have a good idea, all materials or all solids or all objects are made out of atoms, and the atoms are usually neutrally charged, which means it has a positive core, the nucleus, and electrons orbiting it. So when I draw it as a plus minus, I'm drawing an atom and I'm saying that this is neutrally charged, plus minus. So they are all made of plus minuses here. Alright, but to take note, the electrons are the ones that can be removed or added on. Alright, the nucleus is the main core of the atom, and it doesn't usually move. Alright, so just take note of that. When I'm removing electrons, I'm drawing it out. So I have a applet here to show you. Alright, as you can see, you have a balloon here with all the charges. You can see that the balloon is neutrally charged because it has 4 positive nucleus with the electrons surrounding it. So when I bring the balloon over, you see that some of the charges go over to the balloon. Right, this is charging by friction. Now, if I were then to show just the charge difference, you can see then why that the positive charges appear here. The positive charges appear here not because I have extra protons or whatever. It's because my electrons are being taken away. So over this, on the right side of the jacket, it appears positive because I have lost electrons. So therefore I have more protons over than electrons over on this side. While over on the balloon side, I have more electrons than there are protons. It doesn't mean that over here, the balloon, I do not have any more protons. If I show all the charges, then you can see that the protons are still there. Alright, it's just that because I'm only interested in the charge difference, that's why I only show this. So you will see this kind of thing happen even for the pure science. You will combined science, you will see this kind of things being explained later in the later portion of the chapter. Alright, let us first discuss electrostatic charging by friction. Combined science student, please do not pay attention. You are always only for the pure science students. Electrostatic charging by friction only occurs with insulators. Alright, just now, if you recall what was discussed, and the charges are transferred when materials are rubbed together, and there must be two different materials. Now remember that only negative charges or electrons are transferred and not the positive charges. Right, once the electrons are transferred, they are not able to move freely within the material. So this only happens with insulators. Now, you are gonna definitely ask this question, so I'll just address this. How do I need to know what materials will gain electrons, what materials will give away electrons? No, you do not need to know. So what kind of questions they can ask you? I have a glass rod and a silk towel, and I rub those two things together, and the glass rod happens to be positive after that, and the silk is negative. Explain why. So if you are to explain why, then you just say that this is positive because the electrons have jumped from the glass rod to the silk. The silk has more negative charges than positive charges, that's why it's net negative charge. While over here, it has more positive charges than negative charges, that's why it's positive charge. Remember that the protons do not move, they are fixed. They are in the nucleus itself. They make up the core of the atom, so they do not really move. So you cannot say that this fella is positive because the protons, it has gained protons from the silk. You cannot say that because only electrons are the ones that move. So take note of this. Only electrons are the ones that move. Alright, so the second portion, classification of type of charging that occurs is via induction. Now if you recall, induction is a process that works only for conductors and not insulators, because it requires the electrons to be able to move freely around the object. Alright, induction, the root word is induce or cause to happen. Alright, so we induce charges to appear because of the movement of electrons back and forth in the conductor. Right, and this happens without any contact between the conductor and the charging body. Now, there are few ways in which we can do charging by induction. These are the two main examples that are always covered in the O levels. So I just go through a little bit of how it's done. Two metal spheres and a single metal conductor. Alright, charging via using two metal spheres. Alright, so let's have a look at this. So I have two conducting balls in contact with one another, and they are placed on top of insulating stands. Now I bring a negatively charged rod close to those two balls but not touching. There's a small gap here. What happens to the charges on A and B, these two conductor balls? Because they are conductors, the electrons are free to move about. It will cause the electrons to move away, as far away as possible from this negatively charged rod, because light charges repel. Right? Now, can I also then say, and because unlike charges attract, that's why the protons move over to this side? The answer is no. You must remember that the protons do not move. The protons appear here because the electrons are being repelled away from here. Because they are being repelled and moving here, I have more negative charges than positive charge. I induce a negative charge to appear here. Alright, this is the process of induction. So why is there positive charges over here? Positive charges appear here because the electrons are all moving here. I have lack of electrons over here. Because I have a lack of electrons over here, that's why I have more protons than electrons. I induce a positive charge to appear here. So this is the process of induction. Alright. Now, it is important next then that you separate the two before you remove the rod. Because if you remove the rod before you separate the two balls, then once you remove the rod, these charges are going to mix back and you're going to have two neutral balls again. So you must separate the ball first so that the excess negative charges are stuck here, and here there's a lack of negative charges. And then when I remove, I have a net positive charge on the ball, because I have more protons than electrons, and B, I have more electrons than protons, that's why it appears negative. Alright, so I'll just show you the slides. So those of you who need to fill in the blanks can carry on. While I'm explaining, remember I said in an explain question in static electricity, you only say like charges repel or unlike charges attract. And only one of them, you do not say both. You must pick the one that is the correct to the situation. Alright, why I cannot say unlike charges attract? Because you must remember that the protons don't actually move. So while there is attraction here, the protons do not appear because of the attraction between the unlike charges. It appears because there is a lack of electrons, because all the electrons are being moved here. Right, so I'll discuss the charging via a single conductor next. Alright, charging via a single conductor. How it works is pretty similar to the two metal spheres, except that there is the inclusion of an earth wire. So let me just talk about it. If I have a conductor on an insulating stand and I bring a positive charge close to it, then the electrons, then what would you guess is the explanation as to why the charges appear here? Would you say like charges repel and unlike charges attract? Alright, the answer is that you must say unlike charges attract. You cannot say like charges repel. That's why the protons are being repelled by the positively charged rod. The protons do not move because of this. Alright, the protons do not appear here because of this. The protons appear here because the electrons are being attracted, and you should say unlike charges attract. Alright, so once you have this setup where you have excess electrons here, and here you have a lack of electrons, which means you induce negative charges to appear here and induce positive charges to appear here, I connect an earth wire to the conductor. Alright, you are supposed to treat sorry, let me just introduce I don't want to use the hand. So this is the symbol for the earth. You will learn this in current of electricity. So if I were to connect an earth wire here, what the earth does is that the earth is a infinite source of electrons. It also has the ability to take in infinite amount of electrons. Alright, so if I were to connect an earth wire here, because of the positive charges here, all the electrons will want to move up into this conductor, because unlike charges attract. And because they move, they are able to neutralize this excess positive charge. I have more electrons in here, in this charging station here, in this conductor here, than protons. I have more electrons than protons. That's why I have a net negative charge. Then once I have a net negative charge, I break the earth wire connection, which is what happened here, and then I remove the positive rod. Now, if you remove the positive rod before you break the earth wire, if you remove the positive rod, then of course the excess electrons are all just going to go back down to earth to neutralize each other. Alright, so you must break the earth wire first, then you can remove the positively charged rod. Alright, so I have some things here. Treat the earth as an infinite source. You want to copy this. Alright, how then do I get a positively charged? Because the end result of here is that you have a negatively charged object. How do I get a positively charged object? You do pretty much the same, except you bring a negatively charged rod instead. If I bring a negatively charged rod here, the electrons will be repelled to this side, relieving positive charges here. Now, I do want you to take note of a few things here. If you are going to draw 4 negative charges here, please make sure you draw 4 positive charges here. Alright, because I have excess 4 electrons, that means I must have loss of 4 electrons here. Alright, now after I've done with that, what I do then is I connect an earth wire here, and this will cause the excess electrons to move down because they are trying to escape from here. So now once I have moved them down, I have more protons than electrons. I break the earth wire, so what I am left with is a positively charged object. So this is how I charge via induction with a single conductor or two conductors in contact with one another. Now, how does one neutralize charged object? Just now we talked about charging. How do I neutralize the excess charge? Two ways in which we do this: humidity and also heating. Now, in Singapore, we rarely have any gas fire stations or because of caused by excess charge being built up. Alright, in some of the gas stations, you will actually see this metal plate that says touch to discharge before refueling. Right? I don't think we have a lot of that in Singapore because Singapore is so humid, the water molecules actually take away all excess charges. So if you are very negative, then water is a good conductor of electricity. You are very negative, then the electrons are taken, the excess electrons are taken away by the water molecules. If you are very positive, then the water molecules will actually give the electrons to you to neutralize you. So humidity will actually neutralize you quite quickly. Heating also does the same. Heating, what it does is it ionizes the air. It causes the air to separate into electrons and protons, and therefore I have a lot of negative charges and positive charges flying around, which can either give electrons or take electrons for the positive charge. Alright, so heating will also cause neutralization. And the very final way we can neutralize charged objects is via connection to the earth wire. Alright, any excess electrons will be pulled away down to earth. If I have a positively charged electrons, conductor, then the electrons will actually move up to neutralize the charge. So if you have excess charge, earthing it will cause it to go back to neutral. Alright, so all of these are all pure science. Induction, charging by friction, and also neutralizing, the combined signs, we will only start paying attention now from this portion onwards. Okay. Right, for this portion of the question, everyone should be listening in, inclusive of the combined science students. So have a look at the questions in your slide. You have a negatively charged conductor being suspended on a string and being brought close to a metal plate. Metal plate meaning it's a conductor. Alright, and then when it's closed, and this metal plate is connected to the ammeter and then to the earth wire. So the question is, why does it have to be on a string, and why a deflection is seen? Now you haven't learned exactly what an ammeter is. An ammeter is a meter that has the ability to measure charge, or when charge passes through it, it deflects or shows a reading. Alright, you encounter this a little bit more as you are doing your practical. So why does the conductor have to be suspended? Because you do not want it touching any other surface which will cause it to then lose its charge before it reaches or is brought close to the metal plate. Alright, and why a deflection is seen? Alright, so I just need you to remember this is an explain question, and explain questions I already mentioned many times is only either light charges repel or unlike charges attract. So in this case, which option would you choose? Light charges or unlike charges? You should mention light charges, because remember, only electrons or negative charges are the one that will move away in the direction here. So light charges repel and the electrons are repelled from the conductor down to earth. That's why a deflection is seen here. Right, so I'll leave the answers here for you to fill out the blank. You can pause the video anytime you need. Right, the next portion is on electric fields. Now this is applicable for all the sciences, combined and pure, so please make sure you listen in. Alright, this is what are the learning outcomes for this portion on electric fields. So previously when you saw the student or the kid rub the balloon against a hair, you can see that he had some charges. This is the exact same thing that happens when you're walking in an aircon place, especially in a shopping mall, and you are the kind who will drag your feet. Right, then you have a lot of charge build up, and then you have static electricity between you and your friend if you are nearby to them. Alright, so the main point is that there will be forces felt. Light charges will repel and unlike charges will attract. Alright, and this force forms the basis of electric fields.
Right, the force experienced by charges between charges is called an electric force. Alright, they don't have to be in contact, they are non-contact forces. You learn this in chapter 2 or chapter 3 on Newton's laws about forces. Alright, the region around which a charge will experience a force is called the electric field. Now, so this, I put a star here because you need to remember this word forward. Now, this electric field portion looks similar to another field that you have learned, is the gravitational field. So a gravitational field is the region in which an electric charge experiences an electric force. In gravitational field is a region in which not a charge but a mass experience a force. Alright, later on you learn about magnetic fields as well. So all the definitions are the same, just change the item that feels the force. For gravitational field is mass, for electric field is charge, for later on magnetic field is magnets. Right. Another important point is that later on I will show you how to draw an electric field, but you illustrate using field lines with an arrowhead to indicate the direction, and the direction in which we draw the electric field line, this is important, is the direction of force that is felt on a small positive charge. Right, a small positive charge. I have it over here. Alright, so let's have a look at how we would draw the electric fields. So let's say I have a positive charge just here. If I place a test positive charge here, how will this test positive charge, the pink one, move? Because of this fella, he will move away in this direction, because light charges repel. If I place it here, he will move away in this direction. Place it here, he will move away in this direction. Place it here, move away in this direction. All you need to do then is to draw these field lines. Right? If it's at an angle here, it will move away in this direction. So just draw. Right? Some important things to take note of: the field lines should not cross one another, because if I place it here, it will only move in this direction. If I place it here, it will only move in this direction. There is no situation where actually the charge will move here and then move. If I place it at another spot, it move in this direction. Right? So just take note of that. So this is how the electric field of a positive charge will look like. What happens if I have a negative charge then? If I place a positive charge here, it will be attracted, because unlike charges attract. I place it here, it will be attracted. I place it here, it will be attracted. So again, very simple, you just draw. And all the arrows pointing inwards, because that's where the force that is felt on a positive charge. Now you need to remember these two, positive and negative here. Now you also need to be able to draw for me the combination of these two. How will they move? So if I were to have a positive and a negative charge here, and I place a test positive charge, the pink one here, how directly in the center of them, how will they move? Right, they will move in this direction. So I will just need to complete the line like so, a straight line. Now what happens if I place it slightly displaced here? Right, a few things that you will need to take note. The closer you are to the charge, the greater the force that is felt between them. So this fella will feel a greater force of repulsion, while the force of attraction here is weaker. So that's why when I place it here, there's a tendency for it to move out here first until it reaches the middle point. Then the force of repulsion and the force of attraction is the same. And once I move closer to the negative, then actually it will become closer to over here. So you can see that it will take a curved line here. Alright, so just complete it. Alright, please make sure you draw it a little bit nicer, make it symmetrical. Alright, so if I place the positive charge here, then it will forever be repelled, because it's closer to the repulsion point than it is to the attraction point here. So it will always be repelled. So this line maintains, this line also maintains. Alright, so this line, what do I have to do? How does it curve? So the force of repulsion, if I place it here, the force of repulsion will actually try to push it up, but at the same time there's a force of attraction pulling it over here. So the curvature will be like this. So it will go like this. So you must remember the curvature will go like so. Alright. What about this fella? Right? This force of repulsion is trying to push it away, but there's a force of attraction pulling it here eventually. So it will push and then it will curve again. The same over here. Push, but then it will curve again over here. So the curvature, the direction of the curvature matters. This is the one that a lot of students make mistakes. Alright. Just some tips to help you remember. The electric field line will always move out from positive, go to negative. So the direction of the field line is always positive to negative. And the if I'm doing a unlike charge, positive and negative here, and I want to draw the electric field between them, then actually remember that the curvature actually follows the direction of the curvature of this one over here. So if you, over here is where students make common mistakes. They will try to figure out where to draw and then they draw it like this. So this one is wrong. Remember that the curvature just follows the curvature of the curve here that you have drawn. Alright, we will now look at how positive electric field will look like and a negative field line will look like. Alright, I'll leave this here for you in case you want to fill up the blanks. Alright, a negative charge, you know how it looks like. I already drew at the back. They look like that and they will all point inwards towards the negative charge. Alright, a few things for you to take note. The strength of an electric field, I put a star here, so important, is indicated by how close the field lines are. So if I look at the same area, let's say I draw a square of the same size and I draw a square of the exact same size over here. Alright, the number of field lines in this is much more than over here. There's quite a lot of field lines here. So these field lines are closer to one another, or the density is higher. This indicates a stronger electric field over here. That means if I place an object here, the electric force felt here will be greater than it is over here. Alright, so just take note, the density tells me the strength of the electric field. Now, what about the field lines of two similarly charged objects? How would the electric field lines between those two objects look like? If I have two positive charges here, remember that your electric field is the direction of a test positive charge. So if I were to place my positive charge here, then my positive will both repel this fella and he will move. That's why my field line is as such. The same goes over here. Repulsion, because light charges repel, so it will move. Now, if I put it in the direct center between the two, so it will repel, so it won't move. So actually there's no force felt in the center here. That's why there's no field lines here. But even if I just place it slightly up above, then actually the force of repulsion will be this way for this charge, and for this charge it will be this way. So the pushing charge will actually cause them to move in this direction. So even over here, just try and imagine the positive charge is repelling this fella over here, while this positive charge is pushing him up here. So the end effect is that he will go here. But the further he gets away from here, the more apparent this, the less the force of repulsion from here. That's why it curves in this direction. Alright, so how would two negatively charged objects look like? Alright, if I replace this with negative, then the only difference is that all the arrowheads will point inwards towards the negative, because remember, test positive charge, and if this is negative, it will attract inwards. So it will all just be drawing inwards. Right, the last electric field line you need to remember or know is the parallel plate. Now imagine I have two parallel plates. One is positively charged, one is negatively charged. If I place a test positive charge directly in the center, then it will feel the force of repulsion from the whole way here. So this fella here will push him here. The charges slightly here will push him this way. The charges just below him will push him upwards. So all of these forces will cancel out and it will move straight in this direction. The same goes for the attraction. The attraction will be this way for the bottom one, this way here and this way here. So it will be attracted here. Now, why does the field line curve at the top and the bottom here? Because there's actually no positive charge here to push it in this direction. So when I place it here, the force of repulsion will cause it to move out. Then once it passes the center point, then it will curve back in. Alright, so you just need to remember a few configurations. One, just a single positive, just a single negative, a combination of positive, negative, positive, positive, negative, negative, and also parallel plate electric field. So this is all that you need to remember. Now, you also need to remember that the density of the field lines define how strong the electric field, the electric force that is being felt there. So the more dense it is, the greater the strength. Alright, so for the combined science, this is actually the end of the chapter for you. For the pure science, there'll be one more portion for you. Alright, we'll be looking at hazards and applications of electrostatics. Alright, first off, we'll cover hazards. Now, hazards basically just boil down to electrostatic discharge. Alright, electrostatic discharge is basically just a fancy word for spark. A lightning is a super big spark, right? From the cloud to earth. Sparks can be dangerous when you have flammable items nearby. Alright, so this can cause fires. So that's why gas stations, you need to be mindful of this. Flammable fumes, anything that can cause fires, electrostatic discharge will be dangerous. And also those of you who are working with making your own PCs, your CPUs, your GPUs, they will come in the anti-static bag, because sparking or electric charge build-up can actually cause damage to electrical equipment. Alright, so let's just go a little bit about how lightnings are formed. Now, lightnings are formed because the thunderclouds get charged by friction between the water and the air molecules rubbing against one another. So the air molecules are moving around, circulating freely, and then they rub against one another, and due to charging by friction, there's charge build up. So in general, the negative charges gather at the bottom, well, because you remember only negative charges move. So these fellas here at the bottom have excess electrons, so they tend to be slightly heavier. You can think of it like that. And then you have an excess build-up of negative charge and an excess build-up of positive charge here. Now, once you have an intense amount of charge being built up, this will cause the air particles to ionize. Now, usually air is an insulator. It cannot conduct electricity. So when the air particles are ionized, what it means is that one electron will actually come out from the air particle, and actually this will provide the pathway for the electrons to travel down. So the whole way all the air particles are ionized and the electrons come out, and it provides a pathway for the lightning to travel down. Alright, so that is how lightnings are formed. Some other hazards: electrostatic discharge that can cause fire and damage to electronics. Now, fires are especially dangerous at gas petrol station, but actually Singapore is pretty safe. Yeah, so it's because Singapore is quite humid. So remember that one of the ways in which we can discharge is via the humidity. So Singapore is pretty safe because we are quite humid. So any excess charge build up even at the petrol station will immediately be discharged. Alright, so especially for all those fuel tankers, if you are on the road, you can see those big fuel tankers driving. You will see a chain that will drag down behind it. So this chain is actually used to discharge or get rid of any excess charge, to prevent any build-up of charge within the tanker, which may cause a spark. And of course, if your spark is on a fuel tanker, then it's going to cause a big explosion. Alright, I have a short video here. I'll link it for you. It is obviously, it looks like winter. So it's not a Singaporean, it's not Singapore. So you can see that the lady is trying to fill up her petrol. She steps into the car. So where the charging by friction occurs is due to the petrol rubbing along the tube as it is being moved from the petrol station into the car, from the petrol kiosk into the car. So there's an intense amount of fluid coming in. So she rub, then you see a spark, and then fire started because there are a lot of flammable fumes around. Alright, so I'll link the video if you want to see the full video later on. Alright, and as I mentioned just now, electrostatic discharge can cause damage to electronics, especially if you are working with hard drives and circuit boards, which may be sensitive to any excess charge build-up. So if you are doing your mobile robotics, you know that all this sensitive equipment comes in anti-static bags, which prevents the build-up of charge. Now, in terms of applications, there are loads of applications for static electricity, but I think the three that is most frequently tested or appears, of course, O-levels can give you something entirely new, but you have to kind of figure it out. But the ones that we know have appeared are spray painting, electrostatic precipitators, and photocopiers. Now, spray painting, how it works is that as you squeeze your paint nozzle, your paint can, as you squeeze your paint nozzle, the paint that comes out gets charged by friction. So they are all leaving with a certain charge. Now, because these charges are all the same charges, and because like charges repel, they will all repel nicely over here. Now, once I have a negative charge over here, and as long as I don't spray it too close, then actually this negative charge that is trying to land over here will also find another spot and land where there's no negative charge. So spray painting provides an even coat lah. That's why lah. Alright. Another way in which there's another type of painting which is called electrostatic painting, which is slightly different. So I'll link this video again later if you're interested. But basically, you see this object here is the one that they're trying to paint, and actually they spray paint like I already run. Alright, and you can see that even if it's not aiming, the back side or the side nearer to you is getting coated with paint, yellow paint. Alright, this is because this whole object is charged oppositely to the paint particles that are coming out. So that's why they curve around and actually go in here, as opposed to without charging the object. As you can see, they show a demo. Once they remove the charge from the object, even if they spray, you see that the coating is not clear. You can see that the back side nearer to you is actually not being covered with the paint, and only the front side is being covered. So this is a little bit more advanced version of spray painting, which is called electrostatic painting. Alright, apart from that, there's also another one called electrostatic precipitators. Now, precipitators are just fancy names for chimney lah, basically lah. Right, so you see this in kind of industrial setting where you have a lot of smoke and gas coming out. So they would like to remove some of these smoke particles as it's coming through the chimney. So as they're coming through, they have this fine mesh that is made up of negative charges, that is negatively charged. So any particles that pass by here will definitely touch one of them and become negatively charged. Surrounding this chimney are plates that are positively charged. Because these particles are negatively charged, they will be attracted, because unlike charges attract and go over here. Now usually there's a holder here which they can remove, and then all the smoke particles do not escape out into the atmosphere but rather be collected and disposed of. Alright, so this is precipitators. I'll show you a quick example of precipitators here. Alright, I'll link the video again later on so you can have a look. So as you can see, as they pass by here, these particles here are being attracted to the plate because they are charged oppositely to the plate itself. So that removes all these smoke and undesired particles from escaping out into the atmosphere. Now, the very last application is going to be slightly challenging. So this is the photocopier. Now, a photocopier, the drum is made up of selenium, or it's coated with selenium. Now, selenium is a photoconductor, which means it only conducts electricity when light shines on it. So, the portions of the drum, this is the drum inside the photocopier that gets light shining on it, it will become a conductor and it will conduct any excess charge. Now, the center of the drum is usually earth, or depending on the situation, you must see the context, because sometimes they may change the context of the question. So what happens is that usually any image is placed on the glass, you have a light shining. The places where there is writing of black ink, the light will get absorbed. But the places where there's white, the light will get reflected onto the drum. And because the light gets reflected onto the drum, and the drum is coated with selenium, this portion here will become conductive and it will discharge any excess charge. So initially the drum is positively charged. They charge the drum positively. So once you have light shining on it, you will lose the excess charge because the center is connected to the earth. Alright, so because of that, then what they do is that they spray paint the areas, or they spray the toner oppositely charged to whatever charge that is left behind here. So in this case, initially it was positively charged, so they spray a negative toner. So the toner will stick only to the places where the light did not shine, and the light did not shine because of it being dark, or the words are here. So because the lights did not shine on it, it sticks to it. Then what they do is then they run the paper over this, and the inks get transferred to the paper, and that's how you get a photocopy of your paper that you want to photocopy. Now, I have a video here just to show you. I'll link this. I find it quite a useful video, so you can take your time to look at it later on. So basically, how the photocopier works is that you place the paper on top, you press the the drum is usually charged with static electricity, be it positive or negative. So they don't specify here what charge is. Oh no, it's negatively charged. And then after that, when you press the start or copy button, then the light will shine. And then all those parts that are white will have light reflecting, and then when light reflects to the drum, it gets discharged. So only the dark places retain its charge because of the photoconductor here, which is selenium. Alright, after which they spray toner opposite to whatever charge is here, and the toner will stick only to these places. And then after that, the drum rolls and presses onto the paper, and the ink will be transferred to the paper, and then usually there's a heat press to melt the ink permanently onto the paper, and then it comes out as an exact photocopy of whatever you wanted. Alright, so that is the end of static electricity. If you do have any questions, please remember you can just contact me by submitting the question on Google Classroom. So I hope the video is helpful for your study of static electricity. Do make sure that you understand all the things that I start and I said are important, because they'll be vital as for your study of electricity. As you know, this is the first chapter in electricity and magnetism, so you will need to have a strong foundation before you move on to the next chapters. Alright, thank you. Bye bye.